Okay, is this working? She going good? Okay, that works. How about here? Who knows? Can't see her. Huh? Hello? Hey, there we go. Alright. Looks like I got that stuff sorted out. That's a good time, good time. Well, yeah, we'll get anyone today, but that's okay. I'm tired as all hell. That's chill though. Just a moment while I get a few things set up and drink more caffeinated beverage. Alright, we're just gonna start over from what we had last time. I don't know what's going on with that stuff. Camera might not be on the entire time, sorry to say. May turn it on in a bit. Just gonna be drinking tea for a bit though. That's alright. I'm excited. We're very close to the end. I really want to be building a multi-threaded web server. Trying to think about what I'm gonna do with that. Wonder how far we're gonna get. If I can serve a web page, I'm gonna do something terrible with it. I don't know what though. Question is, where the heck am I gonna serve or host it? Ain't many places you can get free VPS. Not VPS. How big is it anyway? What do we got here? We got Yeah, we're going to be able to serve HTML at the very least, meaning we can do fully fledged web pages. Does this mean that we can do like output JSON, like XML, stuff like that? I mean, why not? How are we responding to like routing and stuff like this? I don't think we are. I think we're just outputting a single file no matter what. Huh. Well, that's all right though. Still just going to be a moment. As soon as this gets to the 5 mark, I'm going to start though. All right. Well, hey, here we go. Alright, so we're going to start back out with advanced types. The Rust type system has some features that we've so far mentioned but haven't yet discussed. We'll start by discussing new type in general, as we examine why new types are useful as types. Then we'll move on to the type aliases, a feature similar to new types but with slightly different semantics. We'll also discuss the exclamation mark or bang type and dynamically sized types. Oh, can you see me? Hello? Right. Using the new type pattern for type safety abstraction. This section assumes that you've read the using the new type pattern to implement external traits on external types. The new type pattern is also useful for tasks beyond those we've discussed so far, including statically enforcing that values are never confused and indicating the units of a value. You saw an example of using new type to indicate units in listing 1915. Recall that the millimeters and meters struct wrapped U32 values in a new type. If we wrote a function with a parameter of type millimeters, we couldn't compile a program that accidentally tried to call that function with a value of type meters or plain U32. We can also use the new type pattern to abstract away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type. New types can also hide internal implementation. For example, we could provide a people type to wrap a hashmap I32 string that stores a person's ID associated with their name. Code using people would only interact with the public API we provide, such as a method to add a name string to the people collection. That's the only way they're interacting with it. They're just adding a name string to the people collection. It doesn't need to know that we assign an I32 ID to names internal. The new type pattern is a lightweight way to achieve encapsulation and to hide implementation details, which we discussed in Encapsulation that Hides Implementation Details in the section 17. Creating new type synonyms with type aliases. Rust provides the ability to declare a type alias to give an existing type another name. For this, we use the type keyword. For example, we create the alias kilometers to I32, like so. Now the alias kilometers is a synonym for I32, unlike the millimeters and meters types we created in listing 1915. Kilometers is not separate. Wow. Apologies for the reading there. Kilometers is not a separate new type. Values that have the type kilometers will be treated as if they were just an I32 value. Right, and see we have an I32 kilometers, that is the type alias. We have let x of type I32 equal 5, let y of type kilometers equal 5, x plus y, output. Because kilometers and I32 are the same type, we can add both values and pass kilometers values to functions that take I32 parameters. However, using this method, we don't get the type checking benefits that we get from the new type pattern discussed earlier. In other words, if we mix up kilometers and I32 values somewhere, the compiler will not give us an error. The main use case for the type synonym is to reduce repetition. For example, we might have a lengthy type like this, with a box holding a dynamic function with the sen and a static lifetime. Writing this lengthy type and function signatures as a type annotation all over the code can be tiresome and error-prone. Imagine having a project full of code like in listing 1924. Also separately, if you have to change this at any point in time, you'll have to do it after. And if somebody forgets to put something in it, you may have an issue. A type alias makes this code more manageable by reducing repetition. In listing 1925, we've introduced an alias named thunk for the verbose type and can replace all uses of the type with the shorter alias thunk. Right, and here we have a thunk. F is of type thunk. F of type thunk is passed into text long type. Same with the other. This code is much more readable and easier to write. Choosing a meaningful name for a type alias helps indicate your intent as well. Lunk is the code word for a code to be evaluated at a later time, so it's an appropriate name for a closure that gets stored. Type aliases are also commonly used in the result type for reducing repetition. Consider the standard I/O module in the standard library. I/O operations often return a result and handle situations when operations fail to work. This library has a standard I/O error struct that represents all possible I/O errors. Many of the functions in the standard I/O will be returning result, where the E is standard I/O error. And as these functions in the right tray. Right, yeah. So we have a public trait right, which has a function taking in itself a mutable reference, a buffer which is a vector of U8s, or a reference to U38s, returning a result having a U size and an error. Same with flush, doing something similar, and we have these two doing something similar as well, but in a mildly different form. The result error is repeated a lot. As such, standard I/O has this type alias declaration. Alright, so we have standard I/O error. Sorry, we have a standard result of T with standard I/O error, which is just result T without the dash E, or the type and E. So this would just be U size, and we can omit the error. Because this declaration is in the standard I/O module, we can use the fully qualified alias standard I/O result of type T. That is a result TE, with E filled in as standard I/O error. The right trait function signature ends up looking like this. So, yep, we've just omitted the error piece as well as the use standard I/O error. I don't think that's needed. Perhaps it is, who knows, who cares. But we no longer need it at all. In any point. The type alias helps in two ways, which makes code easier to write, and it gives us a consistent interface across all of standard I/O. Because it's an alias, it's just another result of any type with any error, which means we can use any method that works on a result of any type with any error. With it, as well as special syntax like the question mark operator. The never type that never returns. Rust has a special type named bar. Bang, my lord, bang. That's known in type theory lingo as the empty type, because it has no value. We prefer to call it the never type, because it stands in the place of a return type when a function will never return. Here is an example. Something useful for this would be something that you just continually loop on in like a program that needs to just constantly be running one function, perhaps just to check on some value that needs to be changed. I can't think of too many exact uses for this, though. If you find yourself in a situation where you're using a lot of this, maybe you should rethink what you're doing. This code is read as the function bar never returns. Functions that never return are called diverging functions. We can't create values of the type bang, so bar can never possibly return. But what uses a type you can never create values for? Recall the code from listing 2.5. Part of the number guessing game, we've reproduced a bit of it here in listing 1926. We have let guess of type U32 equal match guess.trim.parse, returning OK as a number, outputting a num, or error, at which point it simply continues. A match with an arm that ends in continue. At the time, we skipped over some details in this code. In Chapter 6, the match control flow patterns section, we discussed that match arms must all return the same type. So, for example, the following code does not work. I'm trying to return 5 or hello. Does not work. The type of guess in this code would have to be an integer and a string. And Rust requires that guess only have one type. So what does continue return? How are we able to return from a U32? How are we allowed to return a U32 from one arm and have another arm that ends with continue in listing 1926? As you might have guessed, a continue expression has the type not or never. That is, when Rust computes the type of guess, it looks at both matching arms, the former with a value of U32 and the latter with a value of never. Because never can never have a value, Rust decides that the type of guess is U32. The formal way of describing this behavior is that expressions of type never can be coerced into any other type. We're allowed to end this match arm with a continue, because continue doesn't return a value. Instead, it moves control back to the top of the loop. So in the error case, we never assign a value to guess. Okay. So there are a heck of a lot more reasons for this. If perhaps you could build your own piece in a match statement, perhaps you want something functional to happen, but would like to return in all other cases, instead of returning some weird flag value that you would then check against before returning control back. You could simply create some macro or some function that will return the never type, I would assume. The never type is useful with the panic macro as well. Recall the unwrap function that we call on option values to produce a value or panic with this definition. With this definition, we have an implement option, public function unwrap, matching against self, some value. If we have some value, return value. If we have none, panic, called unwrap on a none value. In this code, the same thing happens as in the match in listing 1926. Rust sees that val has the type T and panic has the type not. So the result of the overall match expression is T. The code works because panic doesn't produce a value. It ends the program. In the none case, we won't be returning a value from unwrap. So this code is valid. Could we write something that breaks match patterns checking abilities? What if we simply had a random macro that outputted a never and did nothing else, so it would just continue on? At which point you could utilize val, where previously the match statement tries to ensure that you don't. Or, well, you couldn't use val because of other type checking, but this takes away a lot of the value of match if you have the ability to do that. Well, it doesn't take it away from it. I'm just saying that this could be a fuck-on that I'm never going to be using, to be clear, but that could be done. Rust sees that yep. This code works because panic doesn't produce value, it ends the program. In the none case, we won't be returning a value from unwrap, so this code is valid. One final expression that has the type not is a loop. Print forever, loop, print, and ever. Here, the loop never ends, so not is the type of the expression. However, this wouldn't be true if we included a break, because the loop would terminate when it got to the break. Dynamically sized types and the sized trait. Rust needs to know certain details about its types, such as how much space to allocate for a value in a particular type. This leaves one corner of the type system a little confusing at first. The concept of dynamically sized types, sometimes referred to as DSTs, or unsized types. These types let us write code using values whose size we can know only at runtime. Let's dig into the details of a dynamically sized type called string, which we've been using through this book. That's right, not reference string, but string on its own is a DST. We can't know how long the string is until runtime, meaning we can't create a variable of type string. or str, not string specifically. Nor can we take an argument of type str. Consider the following code, which does not work. So we have let s1 of type str equal hello there. Rust needs to know how much memory to allocate for any values of a particular type, and all values of a type must use the same amount of memory. And all values of a type must... Yeah, sure. If Rust allowed us to write this code, the two str values would need to take up the same amount of space. But they have different lengths. S1 needs 12 bytes of storage and S2 needs 15. This is why it's not possible to create a value holding a dynamically sized type. So what do we do? In this case, you already know the answer. We make the types of S1 and S2 a reference string rather than a string. Recall from the string slices section of chapter 4 that the slice data structure just stores the starting position and the length of the slice. So although reference t is a single value that stores the memory address of where t is located, a reference string is two values, the address of the string and its length. As such, we know the size of a reference string value at compile time. It's twice the length of a usize. That's it. That is, we always know the size of a reference string. Perhaps not the data it points to, but the reference string itself we do have the size of. To clarify a little bit there, no matter how long the string it refers to is. In general, this is the way in which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. The golden rule of dynamically sized types is that we must always put values of dynamically sized types behind a pointer of some kind. We can combine str with all kinds of pointers, for example, a box str or an RC str. In fact, you've seen this before, but with a different dynamically sized type, traits. Every trait is a dynamically sized type we can refer to by using the name of the trait. In Chapter 17, in the Using Trait Objects that Allow for Values of Different Types section, we mentioned that to use traits as trait objects, we must put them behind a pointer, such as a dynamic reference to a trait, or a box holding a dynamic trait. RC_dyne_trait would work too. To work with DSTs, Rust provides the sized trait to determine whether or not a type size is known at compile time. This trait is automatically implemented for everything whose size is known at compile time. In addition, Rust implicitly adds a bound on size to every generic function. That is, a generic function definition like this. You have a function generic of any type, taking in t of any type. I don't know what I said of any type here, or that's not that. Is actually treated as though we had written this. Oh, okay. So function generic of any type that implements size, outputting any type. By default, generic functions will work on types that have a known size or compile time. However, you can use this following special syntax to relax this restriction. Right, we have question mark sized. Okay. And reference. Yep, because it always has to be behind a reference, so we have to take in a reference here. Okay. Just to keep that in mind. A trait bound on a question size means t may or may not be sized. And this notation overrides the default that generic types must have a known size at compile time. The question trait syntax is meant with this meaning is only available for size, not any other traits. Okay. I guess that does make sense because it's the only one that is there by default. Either you can have anything, or you can have one piece. What meaning does it have? Why would you put it in there if it could be or could not be? That would be meaningless at that point. But size, since it's there by default, you need a way to stop it. That's a good syntax for it. Hey, could have size, could have no size. Also note that we switched the type of t parameter from a t to a reference t, because the type might not be a size. We need to use it behind some kind of pointer. In this case, we've chosen a reference. Next, we'll talk about the functions and closures. Ooh, now for a quiz. Determine whether this program will pass. Right, so we have function expect none taking in x of an option I32. Outputting? Never. Right, so we have a match on x, which will either output some, at which point it'll panic, or none, which it'll output an empty tuple. And we have expect none, and then we put none in, at which point the none value outputs a tuple. The tuple is then output here, an empty tuple. But it's not trying to... I don't think this will compile because we're not trying to output something that outputs never. We're trying to output an empty tuple, which is the type that we are pushing out. Okay, that's fine. As long as this also separately means that we can output any type, which I don't think it does. I hope it doesn't. I really hope it doesn't. This should never output anything, though, is the point of this. But here it is, outputting an empty tuple. So no, I don't think that will compile. If it does, I'm shocked. Unless I forget, and this is not actually an empty tuple. Determine whether this program will pass the compiler. If it passes, write the expected output of the program as if it were executed. Right, so we have a function is equal. We have a t. Which implements equality. Then you have t1 is a reference to a t, and t2, which is reference to a t. Outputting a boolean. As long as e is equal to t1 is equal to t2, trying hello and world. I don't see any reason for this not to compile. We have t of anything that outputs, unless string doesn't actually have that, which I believe it does. I'm fairly certain it does. We have reference t and reference t. Hello and world are perhaps going to be changed into references. I can't remember if this will automatically do that. I'm just going to say false. Or 0. Sure. Got one right. This program does compile. Does not compile. Okay, this one does not compile. I did get this one correct. It will not compile. This one also will not compile. If it's because this does not implement... Because this isn't a reference, right? So this is a string, right? That is the issue. The call to is equal passes the value of type reference string. That means t equals str. However, str is only allowed to be used in such a generic function if t is marked as question mark sized. Okay. This is a reference type, though. Why? This is a... Whatever, sure. Passes values of type reference string. This means t equals string. Okay, yeah, t would equal string, but it is a reference to a string, to an str. But I guess it's an str, not an reference str that we are asking for a reference to. We are asking for a reference to an str. Okay, sure, whatever. Alright. We have one more before the most interesting part of this chapter. Macros. And it's only been half an hour. Advanced functions and closures. This section explores some advanced features related to functions and closures, including function pointers and return enclosures. Function pointers. We've talked about how to pass closures to functions. You can also pass regular functions to functions. This technique is useful when you want to pass a function you've already defined rather than defining a new closure. Functions coerce to the type fn with a lowercase f, not to be confused with the fn closure trait. Thank you for that. The fn type is called a function pointer. Passing functions with function pointers will allow you to use functions as arguments to other functions. The syntax for specifying that a parameter is a function pointer is similar to that of closures, as shown in listing 1927, where we discussed a function add1 that adds 1 to its parameter. The function doTwice takes two parameters, a function pointer to any function that takes an i32 parameter, and returns an i32 and one i32 value. Okay, sure. The doTwice function calls the function f twice, passing it the r value, then adds two function call results together. The main function calls doTwice, with the arguments add1 and 5. We have function add1, x of i32 is being taken in, outputting an i32, x plus 1. We have doTwice, which takes in a function. Yeah, so it takes in a function outputting an i32 and an argument of i32. Let answer doTwice, add1, 5. And that will output 5 plus 1. That'll 5 plus 1, that's 6, plus 5 plus 1, that's 6, that's 12 being output. The code will print the answer is 12. We specify that the parameter f in doTwice is an fn. It takes one parameter of type i32. This is the type signature. And returns an i32. We can call f in the body of doTwice. In main, we can pass the function name add1, the first argument, as the first argument to doTwice. Unlike closures, fn is a type rather than a result, so we specify fn as the parameter type directly rather than declaring a generic type parameter with one of the fn traits as a trait bound. Function pointers implement all three of the closure traits, fn, fnmut, and fn1s, meaning you can always pass a function pointer as an argument for a function that expects a closure. It's best to write functions using a generic type and one of the closure traits so your functions can accept either functions or closures. That said, one example of where you would want to only accept fn and not closures is when interfacing with external code that does not have closures. C functions can accept functions as argument, but C does not have closures. As an example of where you could use either a closure defined inline or a named function, let's look at a use of the map method provided by the iterator trait in the standard library. To use the map function to turn a vector of numbers into a string of vectors. A vector of string, my lord, I'm not able to talk today. Or any time. We could use a closure like this. We have a list of numbers, 1, 2, 3. We have a list of strings. We have list of numbers .iter.mapping, taking an I, which is each value individually, then I to string.collect. So we just output the string collected. Which, yeah, that's what it's equal. Sorry about that. This is strings equal a vector string. A vector of strings that is equivalent to, yeah. Or we could name a function as the argument to map instead of the closure, like this. Right, so we have just the same stuff. List of numbers .iter map. Then we simply pass in to string. What? Oh, that's the map function. Yep, so the function from toString, the toString function, or method, I guess. Method is a function, but yeah, and we are simply passing that into map, the toString function, which will just simply do the same thing, but as a function itself. And then we collect. Note that we must use the fully qualified syntax that we talked about earlier in the advanced trait section because there are multiple functions available named toString. Here, we're using the toString function defined in the toString trait, which the standard library has implemented for any type that implements display. Recall from the enum value section of Chapter 6, the name of each enum variant that we define also becomes an initializer function. We can use these initializer functions as function pointers that implement the closure traits, which means we can specify the initializer functions as arguments for methods that take closures like so. We have an enumerable called status, with a value of i32 or stop. Let list of statuses, which is a vector of status, sure. I don't know what that does. 0 of type U32 to 20. I see. Yeah, sorry. Here we create status value instance using each U32 value in the range that map is called on by using the initializer function of status value. Some people prefer this style, and some people prefer to use closures. I do. They compile to the same code, so use whichever style is clearer to you. I do personally prefer closures. I think they're nicer in other languages. I don't know about the bar syntax here. I kind of like it, but this is a lot more clear, I'll say. Here we create status value. Yep. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases where you might want to return a trait, you can instead use the concrete type that implements the trait as the returned type of the function. However, you can't do that with closures because they don't have a concrete type that is returnable. The following code tries to return a closure directly, but it won't compile. We have returns a closure, outputting a dynamic function i32. Sorry, which outputs an i32. Yeah. And then it just outputs this closure. It says, hey, return type cannot have an unboxed trait object. Are we just gonna box the closure? Sure. Is that it? I like that. Doesn't have a known size of compile time. That makes sense. That's a good reason. Yeah. So yeah, we're just gonna have to put it behind a pointer or some other type of thing, like a box or an RC, something like that. Help return an impl trait instead of a dyn trait if all return values are of the same type. Wrap all of the return values in box new. Yeah, we're just putting it in a box. Good stuff. And there we go. There's the code. This is why I love Rust. Seriously, man. Look at this. Just tells you exactly what you gotta do in a very understandable format. The error references the size trait again. Rust doesn't know how much space it will need to store the closure. And we saw a solution to this problem earlier. We can use a trait object. Yep, we can use a box new as such. This code will compile just fine. For more about trait objects, refer to the section using trait objects that allow for values of different types in Chapter 17. Now let's look at macros. Very excited. Consider implementing a register function that takes a callback in two ways. We have a function, register1 and register2. Register1 takes in CB, which is a function taking in something called event, or a type of event. Register2, however, has a generic function, has a generic f. CB of type f, where f implements function returning of type event, which type signature permits register to take the widest variety of arguments. I believe this one. I believe it's number 2. I don't think they are equivalent, because this is anything which implements fn, which would include a regular fn thing. You could put in something which is of type fn, a freaking event. Whereas here, it must specifically be an fn of type event. This can take in a closure, because a closure implements fn and can take in a type of event. But not here, because it's not saying it implements this, it's saying, hey, you have to be an fn. Okay, yeah, register 2 is correct. Yep, good stuff. Closures with environments can be passed to register 2. Well, only top-level functions or closures without environments can be passed to register 1. Okay, yeah, I guess I was wrong. Closures without an environment can also be passed to register 1. No. Alright, big boy. You have a quiz at the end? Yeah, we got a quiz. I am incredibly tired. I may jump out halfway through this. But it's only been 40 minutes. I can't do that to you. To me, really. We've used macros like printline through this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust. Declarative macros with macro rules, and 3 kinds of procedural macros. Custom derive macros that specify code added in the derive attribute used on structs and enums. Attribute-like macros that define custom attributes usable on any type. Function-like macros that look like function calls but operate on the token specified as their arguments. We'll talk about each of these in turn, but first, let's look at why we even need the macros when we already have functions. The difference between macros and functions. Fundamentally, macros are a way of writing code that writes other code, which is known as metaprogramming. In Appendix C, we discuss the derive attribute, which generates an implementation of various traits for you. We've also used the printline and vec macros through the book. All these macros expand to produce more code than the code you've written manually. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. However, macros have some additional powers that functions don't. A function signature must declare the number and type of parameters the function has. Macros, on the other hand, can take a variable number of parameters. We can call printline hello with 1 argument or printline hello name with 2. Also, macros are expanded before the compiler interprets the meaning of the code. So a macro can, for example, implement a trait on a given type. A function can't because it gets called at runtime, and a trait needs to be implemented at compile time. The downside to implementing a macro instead of a function is that macros definitions are more complex than function definitions because you're writing Rust code that writes Rust code. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain than function definitions. Another important difference between macros and functions is that you must define a macro or bring them into scope before you call them in a file. As opposed to functions, you can define anywhere and call anywhere. Declarative macros with macro rules for general metaprogramming. I'm just going to take a moment. Now you don't see me. Oh no. I'm gone. I've disappeared. Into the mist. Ah. Sorry, I'm just downing some caffeine. Okay. I'm back. Hello. Declarative macros with macro rules for general metaprogramming. The most widely used form of macros in Rust is the declarative macro. These are also sometimes referred to as macros by example, macro rules macros, or just plain macros at their core. Declarative macros will allow you to write something similar to a Rust match expression. As discussed in Chapter 6, match expressions are control structures that take an expression, compare the resulting values of the expression to patterns, and then run the code associated with the matching pattern. Macros also compare a value to a pattern that are associated with particular code. In this situation, the values in a literal Rust source code pass to the macro. The patterns are compared with the structure of that source code. And the code associated with each pattern, when matched, replaces the code passed to the macro. This all happens during compilation. I'm sorry, I did not understand any of that. To define a macro, you use the macro rules construct. Let's explore how to use macro rules by looking at how the vec macro is defined. Chapter 8 covered how we can use the vec macro to create a new vector with particular values. For example, the following macro creates a new vector containing 3 integers. Here we go. We could also use the vec macro to make a vector of 2 integers or a vector of 5 string slices. We wouldn't be able to use a function to do the same because we wouldn't know the number or type of values up front. This shows a slightly simplified definition of the vec macro. So we have macro rules vec, and inside of it, oh, this looks like Lisp. Nice. We have bracketed space, holding in a $, of bracketed space, and inside of that, we have x, which is of type expression, being replaced here. An arrow, a new syntax, new scope. We have let mutable temp vec equal a vec new, and we replace. Then we have this piece running over, I'm guessing, all of the different types. We have temp vec dot push x. Right, so we're simply creating a new vector and then pushing for every single piece the value which is x. And then we return the temp vec. Okay? Note, the actual definition of the vec macro in the standard library includes code to pre-allocate the correct amount of memory up front. And that code is an optimization that we don't include here to make this example simple. The macro export and annotation indicates that this macro should be made available whenever the crate in which the macro is defined is brought into scope. Without this annotation, the macro can't be brought into scope. When we start the macro definition with macro rules, we then start it with macro rules and the name of the macro we're defining without the exclamation mark. The name, in this case vec, is followed by curly brackets denoting the body of the macro definition. The structure in the vec body is similar to the structure of a match expression. Here we have one arm with the pattern, bracketed space, $, bracketed space, $x of type expression. Exiting the bracketed space, we also separately take in star, followed by the equals the arrow syntax, and the block of code associated with this pattern. If the pattern matches, oh, I see. Yeah, so this is a pattern. That's what I didn't get. I did not understand exactly what this is. This is just a pattern. Makes sense. So any expression and anything else. So if we have an expression, we have type x, which is of type expression. And then this must, I assume, be just a copy of that. It must be the same identity. Followed by the associated spec. If the pattern matches, the associated block of code would be emitted. Given that this is the only pattern in the macro, there's only one valid way to match. Any other pattern will result in an error. More complex macros will have more than one arm. Valid pattern syntax and macro definitions is different than the pattern syntax covered in Chapter 18, because macro patterns are matched against Rust code structure rather than values. For example, declarative macros can match against expressions, expert, types, type, and even entire items. Let's walk through what the pattern pieces in listing 1928 mean. For the full macro pattern syntax, see Rust reference. First, We use a set pattern. Sorry, we use a set of parentheses to encompass the whole pattern. We use a $sign to declare a variable in the macro system that will contain the Rust code matching the pattern. $sign makes it clear that this is a macro variable as opposed to a regular Rust variable. Next comes a set of parentheses that captures values that match the pattern within the parentheses for use in the replacement code. Within a $sign, bracket space, is $x expression, which matches any Rust expression and gives the expression the name of $x. The comma following $sign bracketed space indicates that a literal comma separated character could optionally appear after the code that matches the code in the space. Okay, I was wrong about that. Apologies. The $sign specifies that the pattern matches 0 or more, like regex, of whatever precedes the star. So I was kind of right for the star, but the comma was literally just for the fact that you can, like, 1, 2, so on and so forth. Right. When we call this macro with vector 1, 2, 3, the x $x pattern matches 3 times with the 3 expressions 1, 2, and 3. Now let's look at the pattern in the body of the code associated with this arm. You have a temp vector.push within $bracketed space star is generated for each part that matches $bracketed space in the pattern 0 or more times, depending on how many times the pattern matches. Okay, so yeah, this secondary piece up here is simply repeated for every single time this pattern matches for each piece. Okay. Now, let's look at the pattern in the body of the code associated with this arm. Temp.push, yep. The pattern, yep. The $x is replaced with each expression matched, which we call this macro with vec 1, 2, 3. This code, when we call the vec exclamation mark, square bracket 1, 2, 3, so on, the code generated that replaces this macro call will be the following. So we have let mutable temp vec equal a vector new temp vec.push 1, 2, and 3 output temp vec, which will output temp vec back to whatever you are trying to assign it to, or it'll pass it back out of whatever function, so on and so forth. We've defined a macro that can take any number of arguments of any type and can generate code to create a vector containing the specified elements. To learn more about how to write macros, consult the online documentation or other resources such as The Little Book of Rust Macros, started by Daniel Keep and continued by Lucas Worth. Okay? I kind of like the syntax, obviously. The second form of macros is the procedural macro, which acts more like a function and is a type procedure. Procedural macros accept some code as an input, operate on that code, and produces some code as an output, rather than matching against the patterns and replacing the code with other code as declarative macros do. The 3 kinds of procedural macros are custom-derived, attribute-like, and function-like, and all work in a similar fashion. When creating procedural macros, the definitions must reside on their own crate for the special crate type. This is, for example, This is for complex technical reasons that we hope to eliminate in the future. Posting 1929, we show how to define a procedural macro, where some attribute is a placeholder for using a specific macro variety. Use proc macro. We have some attribute, and we have public function. Yep, we have this. The function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. The token stream type is defined by the proc macro crate that is included with Rust and represents a sequence of tokens. This is the core of the macro. The source code that the macro is operating on makes up the input token stream, and the code the macro produces is the output token stream. The function also has an attribute attached to it that specifies which kind of procedural macro we're creating. We can have multiple kinds of procedural macros in the same crate. I'm really curious. If it's called token stream, is this lexing in some way before it passes it out? I don't know what's going on here. Let's look at the different kinds of procedural macros. We'll start with a custom-derived macro and explain the small dissimilarities that make the other forms different. Right, how to write a custom-derived macro. Let's create a crate called hello macro. Honestly, I don't think I'm... Nah. Yeah, okay. Yeah, sure. Yeah, I got this terminal here for a reason. Right. Cargo. What is it? What am I doing? It's going to be called hello macro. Yep. Right. To get the default implementation of the default, right. Rather than making our users implement the hello macro trait for each of the types, we'll provide a procedural macro so users can annotate the type with derived hello macro. Get a default implementation of the hello macro function. Default implementation will print hello macro. My name is type name, where type name is the name of the type that on which the trait has been defined. In other words, we'll create a trait that enables other programmers to write code like in listing 1930. Okay? Oh, that's not going to work because I don't have that installed. All right, yep. All right, so in the file source main.rs, we are going to be using hello macro, hello macro. Separately, we're going to be using hello macro, derive, hello macro. These do not exist. Shame. Couldn't be me. Right? We are then going to derive hello macro. Oops. Good stuff. Still doesn't exist. And we're going to derive that on the struct pancake. Right, here we go. Function main will just say, hey, pancakes dot hello macro. Just going to be running it. Good stuff. The code a user of our crate will be able to write when using our procedural macro. This code will print hello macro. My name is Pancakes. When we're done. The first step is to make a new library crate like this. Yep. Cargo. New. Hello macro dash dash link. Right. Is this fine? Next, we define the hello macro trait and its associated function. Right. Source/lib.rs. Is that? I don't think that's right, man. Yeah, that's not right, but I'm just going to continue on until it tells me it's wrong because it will. And no, that's wrong. I should Doesn't need help. Workspace. Yep, that is correct. I'm just going to move this. So we want this in where? We want this dot slash source. All right. Where did it go? All right, never mind. We're just creating a new file. What am I supposed to be doing? Is this supposed to be the thing we're doing? What are we doing? What are we doing? Really? I'm not this stupid. So we are creating a new crate named hello macro that defines a trait named hello macro with one using our crate. Yep. Code will print. Yep, we're done. First, okay, so I guess we just. All right. The issue is that I just created something instead of doing it. Okay, fine, whatever. Whatever. Right, I'm just going to delete this. Oh. Hello? Why is H not working? Whatever. Sure. Where the fuck am I? What? No, it's not here. Right, fine. Whatever. I'm sure that was very exciting to watch. You're welcome, guys. Alright. So we are going to create a public trait called hello macro. We're going to create a function in this called hello macro. And that'll be all. We have a trait and its function at this point. Our crate user could implement the trait to achieve the desired functionality like so. Use hello macro, struct pancake, and then we implement hello macro for pancakes. Yep. Then we just pancakes hello macro. However, they would need to write the implementation block for each type they wanted to use with hello macro. We want to spare them from having to do this work. Additionally, we can't yet provide the hello macro function with default implementation that will print the name of the type is implemented on. Rust doesn't have reflection capabilities, so can't look up the type's name at runtime. You need a macro to generate code at compile time. The next step is to define the procedural macro. At the time of this writing, procedural macros need to be in their own crate. Eventually, this restriction might be lifted. The convention for structuring crates and macros creates is as follows. For a crate named foo, a custom-derived procedural macro crate is called foo-derived. Let's start a new crate called hello macro derive inside our hello macro project. Okay. We have hello macro derive dash dash live. That's good, I guess. Sure. Oops. Shoot. There we go. Here we are. Our two crates are tightly related, so we create the procedural macro crate within the directory of our hello macro crate. If we change the trait definition in hello macro, we have to change the implementation of the procedural macro in hello macro derive as well. The two crates will need to be published separately, and programmers using these crates need to add both as dependencies and bring them both into scope. We could instead have the hello macro crate use hello macro derive as a dependency and re-explore the procedural macro code. However, the way we structure this project makes it possible for programmers to use hello macro even if they don't want the derive functionality. We need to declare the hello macro derive crate as a procedural macro crate. We also need functionality from the sign and quote crates, as you'll see in a moment. So we need to add them as dependencies. Also, add the following into the targo.toml. What is this? Yeah, I don't currently have Taplo. I don't know. RPC. Whatever it is, I don't have it. Sure. Right, so we need lib proc macro equals true. Separately, we're going to have dependencies of sign, a version 2.0, as well as quote equal to 1.0. Okay. To start defining the procedural macro, place the code in listing 1931 into your source lib.rs file for the hello macro derived crate. Note that this code won't compile until we've added the definition for the impl hello macro function. Right? So inside of our lib.rs, for hello macro derived, we are simply going to add in everything we need. Use proc underscore macro token string. Invalid offset? Oh, that's not kind. Ah, okay, there we go. You're also going to use quote. Nope. Yeah, that's fine. All right. We are going to have proc macro derive hello macro. That is going to be a public function of type hello macro derive, taking in an input of type token string. Why is this not auto correcting? Auto inserting and outputting a token string. Currently, we are trying to construct a representation of Rust code as a syntax tree. So this is essentially just lexing it. Wow. Yeah, we're literally creating an abstract syntax tree. Do we need to get into this? Okay. What is sign? Oh, what is the incorrect PC? Oh. Oh my god, my. Oh, I see what I've done. Mactio again. Okay. Mismatch types? Yeah, we haven't returned anything yet. Alright, build the trait implementation. Not implementations. Why? Ample. Hello. 1,000 of you could do this 1,000 times quicker than I have. I'm not a typey boy. This is why I use Vim. So I don't have. That is not what I wanted. Okay. Cannot find function info hello macro. That is correct. We have not created. That is not something that exists. What is going on with that? I'm just going to LSP restart. Because it's doing some funky stuff. Right. Listing 1931. Code that most procedural macro crates will require in order to process Rust code. Notice that we split the code into the hello macro derived function, which is responsible for parsing the token stream, and the impl hello macro function, which is responsible for transforming the syntax tree. This makes writing a procedural macro more convenient. The outer code in this outer function, hello macro derived in this case, will be the same for almost every procedural macro crate you see or create. The code you specify in the body of the inner function, impl hello macro in this case, will be different depending on your procedural macro's purpose. Can I see what sign is now? Oh, I can. Right, what is this? Sign is a parsing. Yeah, it's parsing a stream of Rust tokens into a syntax tree of source code. So what we're doing is we're interfacing directly with the Rust compiler. We're skipping the. We are taking already pre-lexed code and then doing some work with it before putting it through and creating an abstract syntax tree. I mean, are we creating an abstract syntax tree here with parse? I'd assume. Yeah. And then we're going to work directly with that. I don't know what unwrap does in this circumstance. Oh, yeah, yeah, sorry. Returns the contained OK value. Sorry about that. Forgot about that. Right, yeah, so we're just generating the abstract syntax tree for a pre-lexed bit of Rust code that we're putting in. And then we're going to work directly with the syntax tree. Sure. We've introduced 3 new crates, proc macro, sign, and quote. The proc macro crate comes with Rust, so we didn't need to add that to the dependencies in cargo.toml. The proc macro crate is the compiler's API that allows us to read and manipulate Rust code from our code. The sign crate parses Rust code from a string into a data structure that we can perform operations on. The quote crate turns signed data structures back into Rust code. Doesn't? Wouldn't be surprised if it doesn't. Performs variable interpolation against the input and produces as a proc macro token stream. So it's back to the lexed token stream. I mean, that's not really Rust code. That's a token stream. No, for returning tokens to the compiler in procedural macro, we use into on result to convert to proc macro token stream. Unless token stream is something I'm not understanding. Is token stream just like the string code? The main type provided by this crate representing an ASAC stream of tokens, or more specifically, a sequence of token trees. Yeah? The type provides interfaces for iterating over these token trees and, conversely, collecting a number of token trees into one string. This is both the input and output of proc macro. Okay, so this is, again, just... Okay, sure. That's incredibly cool! That is incredibly cool. Look, maybe every other language does the exact same thing. That's incredibly cool to see. The sign crate parses Rust code from a string into a data structure that we can perform operations on. The quote crate turns sign data. Does it? What's input? Input's a token stream, though. It's not a string. It's an option bridge client token stream. Right, we're deriving clone features, proc macro, diagnostics. So this isn't just like some random bit. Ooh, well, that's a bit further than I understand. Okay. Yeah, we're gonna have to trust it. Alright, the hello macro derive function will be called when a user of our library creates derive hello macro on a type. This is possible because we've annotated the hello macro derive function here with proc macro derive and specified the name hello macro, which matches our trait name. This is the convention most procedural macros follow. The hello macro derive function first converts the input from a token stream to a data structure that we can then interpret and perform operations on. Yeah, okay, so it's not a string, it is just a token stream, as is obvious. This is where, well, not just, I mean, that's just would be a string. It's a token string, which is much more interesting. Where sign comes into play, parse function in the sign takes a token string and returns a derive input struct. Oh my thanks. Representing the parse Rust code. Listing 1932. We show the relevant parts of the derive input struct, where we get parsing. We get from parsing the struct pancake stream. We have derive input, which is a struct taking an ident of type ident, which holds ident pancakes, span, and then here is the I don't know what that is. Right, let's get it to explain it to us, I assume. The fields in the struct show that the Rust code I was right. The fields in the struct show that the Rust code we've parsed in this unit struct with the ident identifier meaning the name of pancakes. There are more fields on the struct for describing all sorts of Rust code. Check the sign documentation for derive input for more information. Yeah, this is pretty simple. That's just a token. Soon we'll define the import hello macro function, which is where we built the new Rust code we want to include. But before we do, note that the output for our derive macro is also a token stream. Return token stream is added to the code that our crate users write. So when they compile their crate, they'll get the extra functionality that we provide in the modified token stream. You may have noticed we're calling unwrap to cause the hello macro derive function to panic if the call to sign parse function fails here. It's necessary for a procedural macro to panic on errors because proc macro derive functions must return token stream rather than results to conform to the procedural macro API. Don't know what that means, or why it needs to do that. That's not an explanation. We simplified this example by using unwrap. In production code, you should provide more specific error messages about what went wrong when using panic or expect? Or sorry, by using panic or expect. Now that we have the code to turn the annotated Rust code from a token stream into a derived input instance, let's generate the code that implements the hello macro trait on the annotated type, as shown in listing 1932. Right. So we got in this lib here, we have impl hello. Sorry. What are you doing? Right. Oh, yeah. Okay. Function. Impl. Oh, hello. Macro. Taking in an abstraction text tree of a reference to some derived input. Good stuff. And outputting. What's going on? And outputting a token stream. Let name equal a reference to ASD, ident. Sorry, it's an identifier. Let gen equal a quote. Oh, it's a macro itself. Good stuff. Impl. Oh, yeah, of course, it's macro. Hello, man. Hello, macro. For hash name. New scope function. Hello, macro. What if I, is this implemented? It is, okay. I might just change my behavior for that. Right. On this function, we simply print line. Why is that not? Sure, whatever. What's wrong with this? It should have told me words. It should, hello? Whatever. Hello, macro. My name is blank. We then stringify. Is there an issue with this? D8. All right, and then gen.into. What does this even do? Oh, whatever. Is that fun? There we go. Thank you. What exactly was the error? Yeah. Unexpected token? That's fine, yeah, right? Oh my lord. That's why. Yeah, that's fine. No errors. Good stuff. God, I'm tired. Right. We get an ident struct instance containing the name identifier of the annotated type using ast.ident. The struct in listing 1932 shows that when we run the impl hello macro function on the code in listing 1930, the ident we get will have the ident field with a value of pancakes. Thus, the name variable in listing 1933 will contain an ident struct instance that, when printed, will be the string pancakes. The name of the struct in listing 1930. Yeah, is that correct? Yeah, that's fine. The quote macro lets us define the Rust code that we want to return. The compiler expects something different from the direct result of the quote macro's execution, so we need to convert it to a token stream. We do this by calling the into method, which consumes the intermediary representation and returns the value of the required token stream type. I don't think I did that. No, yeah, we did. I'm an idiot. Gen.into. Gen is the quote. Yep. Sorry. The quote macro also provides some cool templating mechanics. We can enter hash name and quote, or replace it with a value of the variable name. You can even do the sum repetition similar to the way regular macros work. Check out the the quote crates docs for a thorough introduction. We want our procedural macro to generate an implementation of our hello macro trait for the type the user annotated, which we can get by using hash name. The trait implementation has one function, hello macro, whose body contains the functionality we want to provide, printing hello macro, my name is, and then the name of the annotated type. The stringify macro used here is built into Rust and takes a Rust expression subset such as 1 plus 2 at compile time and turns the expression into a string literal, such as 1 plus 2. This is different from format or println macros, which evaluate the expression and then turn the result into a string. This is a possibility. There is a possibility that the hash name input might be an expression to print literally. So we use the stringify. Using stringify also saves an allocation by converting hash name into a string literal at compile time. At this point, cargo build should complete successfully in both hello macro and hello macro derive. Let's hook up these crates to the library code in listing 1930 to see the procedural macro code in action. Sorry, where was I? Yep. Create a new binary project in your projects directory using cargo new pancake. We need to add hello macro and hello macro derive as dependencies in the pancakes traits cargo.doml. If you're publishing your version of hello macro and hello macro derive to crates.io, they would be regular dependencies. If not, you can specify them as path dependencies as follows. Okay, so to be clear, what we're doing is just creating cargo new pancakes, right? Right. Right? I'm just going to use path dependencies for now. You good? What's wrong? Expected bang. Yep, I'm an idiot. Kind of? Not at all. Put the code in listing 1930. Sure, whatever. Into source main.rs and run cargo run. Where's 1930? 1930, 1930, 1930, 1930. Is this 1930? No, it's not 1930. Here we go. Oh yeah, that's the one that I had previously done. I don't know what I was doing here. Okay, yep. What am I doing? Okay. Unresolved import of declare crate or module hello. Yeah. It would be regular dependencies. If not, you can specify them as, right, we need hello macro dependencies in, yep. Ah, yeah, I'm a fool. Sorry, I'm a fool. It is in the cargo.tom that we are doing this. Yep. So we're not actually publishing it to trace.io. We are doing it here, which will resolve those errors. Clarify what it is saying is not to try and put it into here like a fool. This is a dependency from a different crate, a different project, essentially. And inside of this, we must have, sorry, in order to include these things, we must have that in our dependencies piece. Okay, makes sense. Sorry about that. Put the code in listing 1930 and yep, it should print. Will this? Nope, of course not. Belt hello manifest for dependency hello macro created by belt read home rest for lemmings macro hello macro hello tone. Yeah, I don't have that. Sure, what about that? Nope. How about that? I must have messed up somewhere. Sure. Yeah, that worked. Okay. Okay. That's funky. Yep. Could I just do this? Does it have to be? This would be incredibly dumb if I could. Could I just say dot dot slash? I mean, that is the path. Yeah, that works. Well, maybe it does. Who knows? Will it fail here? Let's just check. Yep, that's fine. Right, so, yeah, that's fine. Right. The implementation of the hello macro trait from the procedural macro was included without the pancake trait needing to implement it. The derive hello macro added the trait implementation. Next, let's explore how the other kinds of procedural macros differ from custom derived macros. Right? We have attribute-like macros. Attribute-like macros are similar to custom-derived macros, but instead of generating code for the derive attribute, they allow you to create new attributes. They're also more flexible. Derive only works for structs and enums. Attributes can be applied to other items as well, such as functions. Here's an example of using an attribute-like macro. Say you have an attribute named route that annotates functions when using a web application framework. Right, so we have route. Yep, slash on index. Yep. The route attribute would be defined by the framework as a procedural macro. The signature of the macro definition functions would look like this. We have a attribute named proc macro attribute implemented on, yeah, right here is a definition. We have two parameters of the type token string. The first is for the contents of the attribute, the get slash part. The second is the body of the item the attribute is attached to, in this case, function index. The rest of the function is body. Other than that, attribute-like macros work the same way as custom-derived macros. You create a crate with the proc macro crate type and implement a function that generates the code you want. Secondarily, we have function-like macros. Function-like macros derive macros that look like function calls. Similarly to macro rules macros, they're more flexible than functions. For example, they can take an unknown number of arguments. However, macro rules macros can be defined only using the match-like syntax we discussed in the section Declarative Macros with Macro Rules for General Metaprogramming earlier. Function-like macros take a token string parameter, and the definition manipulates that token string using Rust code, as the other two types of procedural macros do. An example of a function-like macro is an SQL macro that might be called like so. Oh, okay. So we have let SQL equal SQL, which is a macro, taking in select all from post where ID equals 1. This macro would parse the SQL statement inside it and check that it's syntactically correct, which is much more complex processing than a macro rules macro can do. The SQL macro would be defined like this. We have a proc macro function, public function SQL, taking an input of token stream and outputting a token stream. The definition is similar to the custom drive macro signature. We'll receive the tokens that are inside the parentheses and return the code we wanted to generate. Right? And I think that's about it for today. I'm sorry, guys, I'm half an hour early, but I'm incredibly tired. I don't know if I could do this quiz. Sorry. Anyway, had fun. I'm really enjoying this. I love that. That is very fun. I'm gonna end now. Goodbye.